Not too bad, I hope. Not bad. That's good. Pre-show, that's good. For better than midterm, yeah, I agree. That's good. For the for hardware computer engineers, like non-software ones, do we have another? I was just thinking about it today. Do we have another like coding course? Like there's like this is like a coding software engineering course, right? 528. I wonder, do we have any more of that? I forgot to like I looked browse through it, but I don't think we have any more like we have a course called Advanced Algorithms that you can take in next year. You can pick it as an elective in fourth year. Oh, I see. Okay, yeah. Like as one of the professional courses. Yeah. Yeah, Advanced Algorithms seems like, yeah. But I don't know, would you call 428 a coding course? Like I guess it is a coding course, but like we don't do that much coding. Our labs are coding, obviously, but I don't know if I would call 428 a coding course. Yeah, it's a computer science course. Yeah, for sure. Anyways, that's just that's just definitions of things. That's fine. Let's begin with our actual thing. I will switch the camera view in 1 second. I will just open up COE 428 live note. Okay, and then you see me. Hi everybody. Hopefully everybody's doing good. As you can see, you know, where I'm recording, by the way, in case anybody's gonna ask, which I appreciate, but yeah, we're good. I'm recording. So today I have a bunch of questions planned for us. In fact, I have these topics planned for us. Let me get them from my screen up here. Get them. There you go. I have these topics planned for us. This is pretty much the things. I have an example or two for each of these things. And I can go into more detail on certain things if you want me to talk about things more or stuff like that. This is a pretty complicated course, so if there's anything that you know that you want to talk about, you know, a little bit extra, we can try to discuss that. Also, if I make any mistakes, of course, feel free to tell me what you think is the mistake, because again, this is a complicated course, so maybe I'll make a mistake. But I'm pretty confident about all this stuff. So yeah, we're gonna go in this order, right? We have this here. And we will just sort of like I have some examples planned. Certain questions I'll ask for you guys' input on certain things. I have it planned and everything, so we'll go through with that. But hope it's a good thing. Okay, any questions before we get started today? Otherwise, I will start with our heaps question. Oh, and one more thing you forgot to mention. Why is Dijkstra highlighted? No love for Dijkstra. I just forgot to highlight it. There you go. Because I was like highlighting each one if I made a question for it, and Dijkstra was the last one, so I just didn't highlight it because it was done. Notes. You can find my notes at www.tutor.ca/notes. I have all my notes for all my courses here. So feel free to take a look at my 428 notes. Now, actually, you know what? Actually, let me do it right now. I'm gonna just quickly update it. I forgot. I made some updates today, and I think it's not there yet. But also I'm gonna update it tonight still, because I didn't put Bellman Ford. I didn't type Bellman Ford into it properly. Like there's like one sentence on Bellman Ford. So let me add it now before anybody goes there. Let me quickly where is it? Manage versions, upload new version. 428. Okay, so there's a newer version because the last one was from Tuesday. The last version was from Tuesday, so it's been a little while. Oh, it's actually not that long. Tuesday's not that many days ago. Tuesday's yesterday. no, today's Thursday. I got all the days mixed up. But anyways, a new version will come tonight as well, just with Bellman Ford at the end. But everything's there except Bellman Ford. Okay, so everything's there right now except Bellman. So again, visit my notes there. Recording is available on my YouTube channel. I never have a link ready, so just YouTube my name. There we go. Also, that's my name, not Gianluca. Gianluca is the res person who has this account. So you can visit my YouTube channel there for the recording of this, and recordings for lots of other courses there as well. Okay, so thank you. I think that might be a link to my channel. There it is. There you go in the chat. Very nice. Thank you very much. I will copy and paste that. I am not able to copy and paste that. Well, I will just copy and paste it. I mean, I'll put it. Obviously, I know you can't click on a Zoom screen share, but for someone looking at the document after, they can find it there. The document will also be available. It's kind of hard. I guess I'll put it in the description, and if I forget to put it in the description, just someone tell me, and I will do Okay, so otherwise, I think we're good to start going. We'll start with a heaps example, and then we'll move on to other stuff. Now, actually, I didn't quite practice this one, but anyways. So pretty much the first example is do heap sort on this. So that's pretty much it. So let's do this here, right? So heap sort on this linked list, not on the example. Linked lists are on the example. We kind of talk about linked lists through a bunch of stuff, right? Through a bunch of like we'll talk about in hash tables, talk about linked lists on a bunch of different things here. So I didn't specifically have a linked list section. Okay, so heap sort. Let's take a look at what heap sort is telling us to do, right? So the heap sort algorithm is, heap sort this array. So we have an array of things here, right? So we first of all call build max heap. So what's build max heap? Here's build max heap, right? So build max heap is this down here at the bottom, right? So build max heap is you ignore all the leaves, right? And you max heapify all the internal nodes, right? So if you were to build this as a tree, right? If you were to treat this as a tree, you max heapify all the internal nodes. Right, so let's go ahead and do that. Let's build this as a tree. So it would just be 4. So not dealing with any kind of greater than less, not a binary search tree, just a tree, right? So it'd be 4 is the root, then 6, 2, right? So 4, 6, 2. Maybe I'll make that a little bit bigger so you can see a little bit nicer. And if I do anything too fast or too not explained well enough, then feel free to tell me and I will fix it. I'll explain it again. So root, left, right, and then left is going to be 1, and then right is going to be 7, and then left is going to be 4, right is going to be 5, right? I may have made this a little bit too big. I didn't try this practice question before. I may have made this tree a little bit too big, but we'll see how it goes. Let's draw that out just to make sure I have everything in place. So left, right, and then left, right, and then left, right. Okay, I gotta switch colors now. So then this is going to be 6, 2, and 7 will have 0, 9. So 6, 2, and 0, 9. So 6, 2, and 0, 9. There we go. So let me, just for the sake of legibility here, let me circle all these guys so that it looks a little nicer. So we treat it like a heap, or we treat it like just a tree, right? There we go. And we call build max heap on it, right? So that means we ignore all the leaves. That's pretty much what this means. A.length over 2, the floor of A.length over 2 down to 1, right? That just means, right, we only count 7, 1, 2, 6, 4, right? 7, 1, 2, 6, 4, right? This is what we call build max heap, right? This would be a, I forget the definition at the moment. Yeah, let's take a look at the definition together. I forget the exact definition at the moment. Let's see it. 428. So this is helpful. Binary trees. There it is. Okay. So let's see the definition. A binary tree, you said complete. So this would be complete. A binary tree is complete if all levels except possibly the last level are completely full and the last level has all its nodes to the left. That is complete. Yes. Complete, not full. Yeah. That sounds right to me. So here's a little diagram that's going to just helpful with if something's complete and full. So this is a little diagram from my notes here. The blue is what you would do to fix it. So the blue is not part of the actual graph, right? So the blue is what you do to fix it, to fix the thing that's missing from it, right? Yeah, there you go. To make this full and complete, you just move that there. Anyways, so yes, this is complete but not full. Yeah, okay. Is complete the same thing as balanced? When would they be different? I mean, I don't think they actually are by definition the same thing, but if something's balanced, then yeah, I think the point is that you want it to be like approximately full or approximately complete. Let me look at the definition for full. Full is if each node is either a leaf or exactly 2 children. Yeah, what do you think is wrong with the heap? Yeah, so you're thinking of a search tree, right? So what I'm gonna do is I'm gonna max heapify it, right? So I'm gonna call max heapify on this right now, right? So it's gonna become a heap, right? It's gonna become a heap. But immediately, if I just interpret this as a heap, right, or interpret it as a tree, it's just a tree. But then I'm going to turn it into a heap by calling Max Heapify on 7, 1, 2, 6, and 4. Yeah, that's right. Yeah, it's not a heap, it's just a tree right now. Okay, so let's go ahead and do that, right? So again, that's what it means. That's what this step means, right? You pretty much, this is just a, you know, code for, we just skip all the leaves, because there's no point in calling Max Heapify on the leaves, right? Because the leaves, there's no children, so there's nothing to move. So let's call Max Heapify on 7. So if I call Max Heapify on 7, the blue is like what you do to fix it, to fix the thing that's missing. That's what the blue represents in my, yeah. So calling Max Heapify on 7, right? This would become, well, that's actually still 0, 7, and 9. So let me just be clear here, right? This is calling Max Heapify on the 7 node, right? And then now we've done that. So now I'm going to do the same thing. I'm going to call Max Heapify on 1, right? So Max Heapify on 1. Heapify on 1, right? And Max Heapify on 1 would put a 6 here and a 1 here. Okay. Then I'll call, oops. Then I'll call Max Heapify on 2, right? Heapify on 2. And that would put a 5 up here and a 2 down here, right? And then again, we call Max Heapify on 6, right? Oh, wow. Immediately one node is causing me trouble here. Sorry about that. And sorry for the quick, like, movie effect there. You're calling it in order of lowest to highest in the tree. Yeah, exactly, right? So it's just like this order here. It's this order here. But yeah, from 7, 1, 2, 6, 4. Yeah, exactly. Yeah, lowest in the tree. So it is being recorded. Yeah, this is being recorded. Yeah. We are sorting from the bottom of the tree to the top tree. Yeah, it's not exactly like I'm sorting an array at the moment. I'm just making it a heap, and I start at the bottom and go up. That's correct. I start at the bottom and go up. I haven't, like, I'm not sorting the array just yet. Like, the array is not sorted, but I'm creating it into a heap. So Max Heapify, I'm going to call it on 6. So calling it on 6 would, of course, make this a 9, and this is 6 over here, right? And then finally, I'll just do this one to the side over here. So this is Max Heapify on 4. And then this would, of course, become a 4, and this would become a 9. Okay, something's up. Something's up here immediately. So I think when I call Max Heapify, I call it on, yes, I'm doing something a little bit wrong there. Okay, this used to be the largest. Okay, yeah. I'm making a mistake while doing this. Okay. Let's see. I think I know what I'm doing. Okay, so the mistake that I made is that when I call Max Heapify, right? At the end of Max Heapify, if I do an exchange, I call Max Heapify recursively down the tree, down the tree like this, and I have not been doing that. So let's try that again. So I call Max Heapify on 7, right? Nothing's wrong there, because then I would call Max Heapify here. So you see, I call Max Heapify on 7. It would do the swap, and then I have to call Max Heapify at this point recursively on what used to be the largest. So it's going to be Max Heapify, right? Heapify on 7. But that doesn't actually do anything at this point, right? That doesn't actually do anything. I'm calling Max Heapify. So nothing's wrong there. Then I call Max Heapify on 1, right? Which does this. This is correct. And now I call Max Heapify on 1 again, but the new position of 1. Because remember, I should remember, this is the thing I forgot, is that when you call Max Heapify, you recursively call it on whatever used to be the largest node. So this used to be the largest node, so now you call it on that again. So now I'll call Max Heapify on 2, right? And then, so I'm going to call it on 2 again now. Max Heapify on 2, right? Again, nothing's wrong there. So that's why, like, I didn't notice until the end. So now I call Max Heapify on 6, right? Which is good. I do call Max Heapify on 6. So notice this used to be the largest node. And so now what I have to do is I have to call Max Heapify on it, again, because it used to be the largest node, right? And it actually does something now. calling Max Heapify on it. So this is not what we get, right? Calling Max Heapify on 6 is going to give me, there we go. Calling Max Heapify on 6 is going to put 6 over here and 7 over here. And now I'm ready to call Max Heapify on 4. Technically, I should call Max Heapify on 6 now. So just to be fully clear, I should call Max Heapify on this, but it doesn't do anything by doing that, right? Calling Max Heapify on 6, calling Max Heapify on a leaf doesn't do anything. And then finally, our last, well, actually there's probably 2 more steps, but the last main step is going to be here, not Max Heapify 6 anymore. So I'll call Max Heapify on 4 now. So Max Heapify on 4. And then that's going to give us a 9. And it's going to, sorry, 9. Yeah, that was a 4. So I'm going to put a 9 here. And it's going to be a 4 here. And now I have to call Max Heapify on 4, right? Because you just recursively keep going on what used to be the largest. So I'm going to call Max Heapify on this now. Get rid of that. Right? So I'll call Max Heapify on 4. Sorry, I'm zigzagging a little bit here, but whatever. Max Heapify. And so calling Max Heapify on 4 means 7 goes up and 4 goes down here. And now I call Max Heapify on 4 again, right? I keep recursively going down. So I call it on here again. Yeah, I am recording. I'm not recording on Zoom, but I'm recording myself. Don't worry. Yeah. Like I have my own recording thing here. So, and I will answer your question in a second, Parthraj. Then the final one here is going to be Max Heapify for one more time, right? Max Heapify for one more time. So it's going to be a 6, and it's going to be a 4 here, and then technically there's one more Max Heapify 4, but it doesn't do anything, right? Because you're Max Heapifying the leaf. You don't really have to. I don't think you have to show the last Max Heapify because that's not really. It doesn't do anything, right? So we have that there, and there we go. And that finally is our heap built, right? Yeah. So where I'll post the recording is on the YouTube channel. That link. Someone posted the link above. I wish there was some way I could pin a link in the chat, but I don't know how to do that. So I'll just. Yeah. So. Yeah, that's true. Someone just said, by the way, Max Heapify X is not where the is the index, not the key. That's true, but just I think it's okay to say here. Yeah, would they want to see? Yeah, that's true. What the actual function call we are doing is on the index, so not the index 7, but on the node 7. So I should put the word node after all these things, before all these things, right? Node 7, node 1. I'm not going to do that, but yeah, it should be the word node there. Okay. So there we go. So that is that. Okay, Parthraj asked the question. So for building Max Heap, don't you call Max Heapify for each new node you add instead of calling recursively and on the already finished graph? Yeah, so you can do it. There was 2 ways to construct it, but if we're following the heap sort procedure, right? The heap sort procedure, it would be like this. You already have an array and you call build max heap on it, right? And you call build max heap on it. Like that's the heap sort procedure. You can say build max heap is going to go from array length over 2, right? So these nodes, it's going to be, you're interpreting it as a binary tree, and then yeah, from there you move on. Okay, great. So that's building the heap, and now the heap sort actual algorithm. We finished this, and we just have this last step here, right? We just have this last part here. So we have our heap. 7 isn't 7 the 5th node? Yeah, I think so. In this case, yeah, 7 is the 0, 1, 2, 3, 4, 4th node. It depends on if you start at 1 or 0. Just label it whatever you start at. Yeah. So yeah. Then to do the actual heap sort, right? We are going to build max heap, and then we can for I equals a.length down to 2, right? So we start at the length of the array. Let me get the actual array here. We start at the length of the array, right? So here's our array. I guess actually I should organize it like the array we see here. So the array we see here is going to be 9, 7, 5, 6, 6, 4, 2, 1, 2, 0, 4, and I'll just put commas between all that. So that's the actual array here, and you just take it, you just read it in order, right? Like this. That's how you read it. And so notice it's not exactly sorted at the moment, but what you do is you exchange A1, right? A1 would be, so I guess we'll say we're starting at 1 here, right? So this is A1, right? With AI, so AI is, first of all, the length, so it's going to be 4. So you switch the root with the node, with the last leaf, right? Pretty much with the last leaf, right? Decrease the heap size, and then call Max Heapify on the root there. Yeah, on the root. So I'll just show what that is in action. You're going to do this recursively, right? Well, not recursively, but in a loop, I mean. So what that's going to look like is, now I'm going to use green lines to show that we're actually in heap sort now. So next step of heap sort. We will take this, and what we do, come on, there we go. What we do is we replace 4 and 9. So essentially, you can think of it like we just take away 9, right? We take away 9, we put 4 up here, right? And what happens is the array now looks like this. Looks like this. So I'm going to take away the 4, I'm going to put it at the front, and then there's just 9 at the end. But importantly, that is our heap. That is our heap now. 9 is just in the array, but it's just at the end, right? So the length of our array is that long, but the length of our heap is this long, right? So here, the heap is the entire length. And then what I'm going to do is I'm going to call Max Heapify on this now, right? Max Heapify the root, right? So Max Heapify the root. It's not letting me type for some reason. Max Heapify, 1, the first node, right? Okay, so it should be a little consistent, so I'll call it node 4. Node 4. But yeah. So calling Max Heapify on this would look like this. Let's see what it looks like. So there we go. So we put a 4 here and a 7 here. And I'm not going to do a bunch of steps. I'll just do this all in one go here, right? So we put a 4 and a 7. It doesn't really matter which one you switch to here. So we'll just take the, I don't know, we'll just take the left one. So we'll put a 4 here and a 6 here. And then call Max Heapify on 4. There, you wouldn't do anything. And so there you go. You're done. That's the end of that. And then you just do this again, right? So you would say, this next step of Max Heap Sort would be remove 9. And then the next step would be, Heap Sort. Next step heap Sort would be remove 7. It's not a function, so remove 7, right? And so I'll just update the array. So the array for this one would now look like this. So it'd be 7, 6, 5, 4, 6, 4, 2, 1, 2, 0. There you go. So that's what the array looks like now. And now heap sort remove 7. So what it would look like is we take this. By removing 7, what I'm really doing is I'm just taking the last leaf, putting it up here, and then putting 7 at the end of the array. Right? So if I copy this now, whole lot of copy and pasting today. There we go. Right? So if I have this, what I'm doing is I'm just taking 7 away, right? Taking 7, I'm replacing it with 0. I'm taking 0 out from the end here and putting 7 at the end. Yeah, putting 7, not 7 at the end. Sorry, 7 here. There. That's where I'm putting 7. Where 0 used to be. Putting 7 where 0 used to be. Yeah, someone said you always take the left case. Yeah. So would it make a difference if I always left case according to the algorithm? Yeah, is it according to the algorithm I would take the left case? Let's see. Is that what Max Heapify says? Equal. Yeah. Yeah, I guess I would take the left case. Okay, let's just make it completely accurate. So I would take the left case here. So, oh no, this is the left case. Never mind. I thought I did the right case. There you go. Okay, we're good. It is left case. Okay, we call Max Heapify again, right? We call Max Heapify again here. Okay. So calling Max Heapify on 0, on node 0, I should say, right? Node 0. Oh my god. One node is nice, but for copying and pasting, it does not like to agree. node 0. Maxi on node 0. So that looks like I'm going to put a 6 up here, a 0 here. So I'm going to put a 6 here, and a 0 here, and I'm done. There's my Max Heapify. And then next in, I guess I'll keep updating the array. Okay, so the array would now look like 6, 6, 5, 4, 0, 4, 2, 1, 2. And now what I'm going to do is I'm going to keep going. I'm going to say heap sort would be remove 6, right? So to remove the 6, again, what I do is, I wish OneNote would agree with me one day. Come on. There we go. There we go. Okay. So removing 6, what that looks like is I take the, I take 6, replace it with 2, take 2, replace it with 6, and then I make the array smaller. That's the whole point, right? So I keep just sort of like flipping the leaf, the last leaf. So I remove that leaf and then make this a 2 here. I replace the root with the last leaf and then just make the array a little smaller, right? And then so this leaf is not there anymore. Call Max Heapify again, right? So Max Heapify on node 2. And so this would look like this. I probably should have made a shorter example, shouldn't I? So then this is going to be a 6. This is going to be a 2. This is going to be a 4. This is going to be a 2. And we're done. So then I will just keep going here, put this like this. All I've done is I've reordered. So it's going to be 6, 4, 5, 2, 0, 4, 2, 1. There we go. Next, I'm going to remove this, remove 1. We can keep going. I could, like, I don't know. Do you guys want to see me go all the way to the end for this question? Yeah, I was gonna say, do you guys want to see me go all the way to the end, or does this sort of make sense? Eventually, you're just gonna get rid of all the nodes, and then you'll have a list in order from smallest to biggest. So does anybody like me to see, like, continue to do maybe a few more steps? Let me know. I'll do this last one here. Otherwise, I'll move on just for the sake of time. Well, I can tell you for sure the final result. I mean, the final result will be an empty heap, right? Because there'll be nothing left in the heap. And then you would have it in ascending order, right? It would be going from, well, it'd be 1, 2, 2, 4, 5, and 2 4s, I guess. No, 0, 1, 2, 2, 4, 4, 5, 6, 6, 7, 9, probably. Yeah, there you go. And there'll be something like that. So let me just remove 1. So removing 1 would be remove 1, but make that 1. And then our final array, oops, our final array here would have a, sorry, we replace 1 with 6. We replace 6 with 1. And then we make this a no color there. And then I'll just say ... Eventually you have no array, sorry, no heap, no heap. And your array is entirely just whatever this is sorted. 0, 1, 1, 2, 2, 2. There's no 3, so 4, 4, 5, 6, 6, 7. It looks right to me. I don't know. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Yep, there you go. Okay, we got a bunch of questions. So the heap would still exist. It just wouldn't be in the same order. Well, the heap is how much. Yeah, the array. Well, the heap is how much of the array we are allocating to be a heap, right? Notice like this part is in the array, but it is not in a heap, right? It's just stuck at the end of the array there, right? This is the heap. We're saying this is a heap, so it is a heap, right? But at the end of it, we're going to have nothing highlighted in yellow by the end, which means there's going to be no heap, right? Everything will be removed from the heap, and then it'll just be an array in reverse order. Since the array had the heap property before, but it's like this just without the heap property. The array, yeah. There you go. That's not my water. Okay. So there's my heap sort example. I should have made it shorter. I apologize for that. That's a long example. But hopefully the Max Heapify made sense, how we construct it. And then after this, it's just a lot of repetition to get to the end there, right? Okay, so carrying on, let's move on to hash tables. I have an example for hash tables, which looks like this. Mostly the hash table example I'm going to do is like a probing example. That's the example that I have. Okay, so ignore this stuff. So this we don't care about. This is from the textbook. Just ignore that. That's fine. Okay. So consider inserting keys, those keys, into a hash table of length 11 using open addressing with the auxiliary hash function h prime of k equals k. H prime of k equals k. And h1 of k equals k. Yeah, for the next part. And h2 of k, equals 1 plus, I thought they were going to give me a mod there. K mod m minus 1. There we go. We want to illustrate the result of inserting these keys using linear probing, quadratic probing, and double hashing separately. We're just going to do the same thing, but for the 3 different kinds of probing there. So first I want to just illustrate what's happening here, right? So we have a hash table with 11 different slots, right? So let me try to make this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There we go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There you go. So it's just a little too big. And just ignore this end here. Just, ignore that there. Okay, so we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there's our array. We have the 3 different kinds of probing. So we're going to start with linear probing. So what linear probing is it's a way to deal with collisions that are happening in your hash table, right? So let's say your hash function is h of k equals k, right? Like that's the hash function you're using. Okay, you would want to do that mod 11. So really the entire hash function you're using is mod 11. But what if you run into a collision? What if that's already happening? Like what if there's something already in that slot? Then you have to choose a different slot, but how do you choose the different slot, right? So linked list is a way to, you can leave everything in the same slot and just make the slot be able to hold more than one element. But probing is a way so that every slot still holds one element, but it's just how do you decide where's the next slot you go to, right? When you're trying to insert something. So that's the idea about probing here. So probing has a formula, right? So the formula for linear probing is you say, okay, so the slot that I'm going to assign k to after I attempts, so I starts as 0, after 0 attempts initially, and then you start after 1 attempt, after 2 attempts, right? And so on, is going to be k prime h plus I, k prime k, h prime k plus I mod capital N. That's linear probing. What I'm going to put in the blue box here, that's always true for linear probing. Okay, h prime of k is what your particular hash function is. It could be anything. It doesn't really matter what your hash function is. And you can do linear probing with it by using this formula. Because you're saying I is the number of attempts you've made. So I is the number of attempts you've made so far. Right? So with this, we're going to do that. We're going to use this here. So with our particular example, our exact hash function is hki equals h prime of k is k for our question, right? K plus I mod n, right? K plus I mod n. And yeah, there we go. So that's what our hash function is for, mod 11. Mod 11. There we go. Because n is 11. That's the thing I missed. So there's our linear probing hash function, and let's try to put some of these numbers in now, right? So putting some of these numbers into this hash table, right, is we start with I equal to 0, right? That's how you always start, because you're saying I've made no attempts yet, so this is my first attempt, so I is 0. So 10. So this is going to be 10 plus 0 mod 11. So 10 mod 11. 10 mod 11 is 10. So we're going to put a 10 here, right? Then we're going to put 22, right? So we're going to try 22. So 22 is 22 plus 0. It's still 0. I've still made no attempts for 22. So 22 plus 0 mod 11 is 22 mod 11 is 0. So 22 goes here. Then we have 31 mod 11, right? So, well, 31, let's be clear. 31 plus 0 mod 11, right? Because, again, I've made 0 attempts for 31. So 31 plus 31 mod 11, right, is 9, if I remember correctly. Yeah, 9. So 9's free. We can just put 31 right there, right? Now 4, it's going to be 4 plus 0 mod 11 is also 4. And now 15. 15 plus 0 mod 11 is 15 mod 11. 15 mod 11 is equal to 4, right? 15 mod 11 is equal to 4. So, or, you know, depends on how you phrase it. But anyways, 15 mod 11 is 4. So that's not good. We already have something in 4. So now, this was with I equal to 0. Now I equal to 1, right? We say 15 plus 1 mod 11, which is 16 mod 11, right? 16 mod 11. 16 mod 11 is 5. And so we can put 15 here, right? So this is equal to 5. And so we put it in the 5th slot. We put 15 in the 5th slot, right? 15 in the 5th slot. Not 16, 15. Because it was k plus I and put k there. So next one is we'll do 28. So we're done with 15. I is now back to 0 because we've made no attempts for 28. So it's just 28 mod 11. 28 mod 11 is 6. So I can just put 28 here. Right. Then I have 17 mod 11. Again, 17 plus 0 because I've made no attempts for 17. So plus 0. So 17 mod 11 is 6. We already have something there, right? So then what I do is with I equal to 0, it was 17 mod 11 equals 6. Now I have to set I equal to 1. It's going to be 18 mod 11 equals 7. And so we're going to put 18 here. A way to visually do this, right? It's easy with linear probing to just visually do this. Is like you try the slot. Like here, we tried 28. It was full. So you go to the next slot and ask, is it full? If not, if it is full, you go to the next slot, right? And you just keep going like this. With quadratic and double hashing, you can't really do that. You can't really guess where it's going to be, right? Oh, 17 out of 18. Yeah. Thank you. Yeah. You can't really like, it's harder to just see where the next slot's going to be, but linear probing, it's easy. You just like find the next slot as you go forward, right? Just find the next one. So we can use that logic for the next one. Like 88 is congruent to 0 mod 11, right? So 88 is 0 mod 11. So I'll put 88 here though, right? Because I just go to the next slot. I don't have to even use the formula for linear probing. I don't really have to use the formula. I just know I'm going to the next slot. Right? With quadratic, it's a little bit different. How do you know where to put the 4? Put the 4 and the 15 in the array thing. Well, so I knew to put the 4 was no trouble because that's our hash function, right? That's our hash function. At first, I make 0 attempts so that's I equals 0. So that would be 4 mod 11. 4 mod 11 is 4, so that's the slot I put it in. I put 4 in there. But then when I try to put 15, I do the same thing. I say 15 plus 0 mod 11, because again, I've made no attempts for 15 yet, so I is 0. So 15 mod 11 is also 4, right? 15 mod 11 is also 4. So they're both being assigned to the same slot. That's the whole point of the I variable, is that, okay, I made an attempt, but now I need to do things differently because that attempt didn't work. So I'm going to set I to 1 now because I've made one attempt. And so that's what I did here. So now it's 15 plus 1 mod 11. 16 mod 11 is 5. And so 15 goes in the 5th slot. Does that make sense? Does that answer that question there? Hopefully. Okay. Yes. Very nice. Okay. So good. So then, so then 88 is easy. Like with linear probing, it's easy to just like look and see it. You go to the next available slot to the right. 59, right, is 4 mod 11, but I can just tell you right away, 59 will go here, right? Because you say 4, 59 is 4 mod 11, but you're just going to keep going to the right until you find an empty slot. And if you go to the end, you loop back to the start. It's mod 11, right? So it cycles. And there we go. That is what it would look like after we insert those numbers into a hash table, which is using linear probing, right? Quadratic probing would be different. Double hashing would be different. Well, actually, it actually turns out that quadratic hashing is actually the same thing, but that's just in this case. But you'll see that we have, it's different how we get the numbers to those places. Anyways, what's the C1 and C2 in the question? Yeah, I think it's the way that the textbook does quadratic probing. They need some extra numbers, but we don't do that in our lecture slides. So I'm just going to ignore those numbers. We can just do quadratic probing how we do quadratic probing. The reason we subtract mod 11 from 15 is because there aren't 15 spaces in the array, right? Whereas the 4 spaces, so we insert it with it. Let me make sure I understand. The reason we subtract mod 11 from 15, well, hold on, we're not subtracting, like, we're not really subtracting mod 11. Like, we're taking 15 mod 11. 15 mod 11 is 4, right? I'm not going to use congruency here, but 15 mod 11 is 4, right? The remainder when you divide by 4, right? And so we do it mod 11 because there's 11 spaces, right? We do it because there's 11 spaces. Yeah. So we can't just directly put it in the 15 slot. We have to do mod 11. But what if that slot's already taken? That's the whole point of the probing, right? That's the whole point of the probing, right? Yeah. Okay. Do you think we're going to have to deal with... do you think we're going to have to be given a way to hash it, or we'll be able to choose which way? Like, given the hash function? Probably given the hash function. But also you can, it's not too complicated. Like, you can just do the division method for making a hash function, which is just, you just mod it by the number of slots, right? Let's say h prime of k equals k plus 1. How would the linear probing change? If the h prime of k was k plus 1, then you would just have a plus 1 here. That's all that would be if h prime of k was k plus 1. And you do the same process, right? It would just be like, you just have a plus 1 there. That's all it is. Everything would be shifted 1 to the right. Linear probing says only the hash function changes, so yeah, that's what said. How does mod 11 on 10 work? Yeah, so like if you divide, yeah, anything less than, so like 10 mod 11, right, is what we're saying. Is that, yeah, so like 10 doesn't go into 11, and there's a remainder of 10. Does that make sense? It doesn't go in at any point, like it doesn't go in at all, and then there's a remainder. Or other way around. I think I did that backwards. 11 doesn't go into 10. There's yeah, but that's the idea. There's just a remainder of 10. Anytime you have, like, you're taking like a number mod a bigger number, then it's just that number. It's just gonna be that. Okay. Yeah, that's also more of a discrete math. Okay, do you think we will be able to choose between methods like linear probing, or will they say use linear probing? No, they might say to use the specific kind of probing. They might say linear, quadratic, or double hashing. So let's so if all the slots are full and you want to store a number, then what do? You can't. You're done. There's nothing else to do. You can't put it in. This kind of collision avoiding doesn't deal with if you have too many things. If it's taken, then you do collision resolution. Yeah, you can't have more keys than array spots. Yeah, with this kind of collision avoiding. I forgot the word. Collision detection? No, that's not the word. Collision handling. There you go. Linked list collisions would allow you to keep going, right? That's why you make your heap array very large to avoid the issue with running out of space. Yeah. Okay, so I'm gonna keep going. So quadratic probing is the next one. Quadratic probing is the next one. So we have quadratic probing. I'm going to show you how similar it is by just copying and pasting this, right? So quadratic probing is almost the exact same thing, but look, you just square it. You square the I. That's everything. That's the whole thing. This is still the same general formula, right? So what we're going to do is we're going to take this array. I'm going to erase these, right? So we're going to insert the same numbers, but this time using quadratic probing. And so remember our auxiliary function, the function they gave us was just h prime of k equals k. So we have our function hki. So where's the key k going to go after I attempts? Is just k plus I squared mod 11, right? Okay, so if there was a collision at 2, you would move to the next spot you would move to would be 4. Like for quadratic, it depends on how many attempts you've already made, though. That's the thing. It depends on how many attempts you've already made. So if you've made 0 attempts, then you would go to the next spot. You'll see, because you would make I equal to 1. 1 squared is still 1. So at first, linear and quadratic will bring you to the same spot, because linear would be k plus 1. Quadratic will be k plus 1, because 1 squared is 1, right? So if we attempt this, right, at first, you know, if you always have to make 0 attempts, then there's no need for the I at all, right? So for 10, I've made no attempts yet, so I is 0. So it's just 10 mod 11. 10 mod 11 is 10. 22 mod 11 is 0. Still goes here. 31 mod 11, right, is still 9. Pretty sure, yeah. 4 mod 11 is still 4. 15 mod 11 is also 4. So now I have to set I equal to 1. But if I is equal to 1, it's k plus 1 again. So 15 is still going to go to this slot. So at first, quadratic probing and linear probing are the same thing. Okay. 28 is 6 mod 11, so that's fine. 28. I is 0 again, right? When you go to the next number, you reset I because you've made no attempts for 28. Now we have, again, 28 is here, right? 28 is here. Sorry, 17 is the next one. 17 mod 11 is 6. So we're already taken. So what I have to do now is I have to set I equal to 1. It's going to be 17 plus 1 mod 11. 18 mod 11 is, oh, sorry. Yeah, 18 mod 11 is 7. Yes, there you go. So I'm going to put 17 here, right? 88 mod 11 is 0, right? 88 mod 11 is 0. So 0 is already taken, so it's 88 plus 1 mod 11. So 89 mod 11 is 1. So it's going to be 88 is going to go here. And now this last one, if I remember correctly, is 4. Yeah, there we go. This last one is going to be, you know, something. So you see here with 59 mod 11 equals 4, right? So I have to try 59 plus 1 squared, right? Mod 11, right? Which is now 5, right? Which is 5. 5's also taken, right? So now I have to try 59 plus 2 squared. Okay, so now this is where quadratic probing and linear probing become different things. Because now look, I'm not just going, so with linear probing, it would be 59 plus 1, then 59 plus 2, then 59 plus 3. For us, for quadratic probing, it's 59 plus 1, then 59 plus 4, then 59 plus 9, then 59 plus 16, 25, right? So you keep adding squares of I, right? And so this is now 63, yeah, which is congruent to 8, right? So, which is, you know, mod 11 equals 8, right? So then we're just going to say that 59 goes into the 8th slot. So it actually turns out that linear and quadratic probing give us the exact same hash table in this case, but kind of for different reasons, right? Hopefully understand the difference in the reason that it gives you different ones there. Okay, so I is the number of attempts taken to place a value in same index in the array. Yeah, it's the amount of previous attempts. I say previous because, like, you don't, on attempt 1, you don't say, this is my attempt 1, I is 1. No, you say, how many previous attempts have I done? On the first attempt, you've done no previous attempts. So I is 0. But that's pretty much it. What did H1? Yeah, that's for quadratic. That's for double hashing. For this is the next one. That's for double hashing. So nothing yet. What if you keep doing it and all the slots are covered? Then there's nothing to do. Then there's nothing to do. Then you can't put it in. It should, I think if you implement this in like an actual computer, you have some way of checking that you've gone through all of them, but otherwise by hand, you just see you're full and you're full. What are the odds of getting asked double hashing? He taught it, he covered it. I'd say, I don't know. relatively high. Not, I don't know about high, but like reasonable for him to ask.
Can I ask a question?
Yes, for sure.
If you go, I didn't keep up with part of the problem at the very
Yeah,
top. So like there's a, I think I saw like other than this function that you wrote here in blue, I saw like something at the top says h1k and h prime k.
yeah,
I know h prime k is just k that you put in the equation here, but
yeah.
I don't know what h1k and h2k are. They
That's
kind of
for
threw me off. So what's that?
that's for double hashing. That's the next thing we're going to talk about right now. That's for
Oh,
double
okay.
hashing, right? Yeah, yeah. But good question. Yeah, double hashing. They definitely were not used so far, right? They definitely were not used here. So essentially, for double hashing, what we want to do is we kind of want to generalize this, right? We want to generalize this to not just be, so this is quadratic probing, double hashing. So double hashing, right? So we have h1 of k, and then we actually have a whole second hash function that we use. And what we do is instead of having, I, some function of I here, right? We get rid of the squared. You just multiply it by h2 of k, right? And still mod n, right? Still mod n. But you do your initial hash function, and then you add I times some other hash function. And this is a little bit of a better way of doing it because I presume it gets rid of the clumping, like the clustering, right? So linear probing has a clustering issue. Everything's going to be clustered in the same spot, pretty much. Quadratic probing has some clustering issue too, and this is the best one to deal with clustering issues. Okay, so double hashing is the next thing we'll do. So in our particular case, they told us these were our two hash functions. So for us, it's going to look a little scary. Let me actually just copy this first. It's going to look a little scary. Actually, I'll just get rid of this. But what our hash function is it's going to be h of ki, right? H of ki, not write it right there. H of ki equals, okay, now big bracket, right? h1 of k is just k, right? K plus I times h2. h2 is 1 plus k mod m minus 1. And then, did I close the brackets enough? Yep, there we go. And then I'm going to mod 11, because it's 11 slots. Yeah, gonna go over. Yeah. So there we go. So this is the formula. This is the general formula for double hashing. This is one more close bracket. Yeah, one more close bracket. Yeah. There we go. Thank you. Yeah. So here we have our general form of double hashing. Here we have our specific form for the question. They told us what h1 and h2 were. And so now, remember, I has the same meaning as the number of attempts that you've made so far, number of previous attempts. And so what we're going to do is we're just going to plug in some numbers. So let's start with this one. Oh, sorry, m. What's m? M is the number of slots, I'm pretty sure. M. What is m? M was 11. Yeah, M was the number of slots. That's just the way they phrased it. Actually, I guess we can call it n for us. We can call it n, right? So it's just gonna be 11. 11 minus 1.
So
M is just what they called it in the question. Sorry, go ahead.
Wouldn't you just write that as 10 then?
Yeah, you would. That's yes,
10?
exactly. Yeah, exactly.
Okay.
I'm just gonna copy it, copy and paste it. But yeah, exactly. That's my next thing. Is like there's no point in writing it as two things. It's just mod 10. There you go. So now we'll go ahead and do this for all the numbers again. So we start with 10. So to begin with, it's 10 plus 0. So ignore all this. Mod 11. 10 mod 11 is 10. No trouble. Then we have 22 plus 0. Ignore all that. Mod 11. 22 mod 11 is 0. Then we have 31 mod plus 0. Ignore all that. 31 mod 11 is 9. So these numbers aren't any different. Then we have 4 plus 0 mod 11 is 4. Okay. 15, right? 15 plus 0 mod 11 is also 4. So 15, k equals 15, I equals 0, then h of k 0 equals, or h of, let's say h of ki, right, equals 4. That's already taken, right? So what we got to do is we got to say, okay, now we have k equal 15, I equal to 1, right? So h of ki is going to be 15 plus 1 times 1 plus 15 mod 10. And then mod 11. And then I'm missing a bracket. So, am I missing a bracket? Yeah, I am. So there you go. So 4 mod 11 is, wait, how is 4 taken? Yeah, 4 mod 11 is 4, right? So we already put 4 there. So then our next one is going to be 15 mod 11 is also 4. So we have to find the next slot. So what I like to do is if you're ever doing this like double hashing, this yellow, it stays constant throughout the same key, right? So if you have to keep doing this, like let's say over and over again, the key is taken, like the spot is taken, this never changes for the same key, right? So just what that is, 15 mod 10 is 5 plus 1 is 6. So it's 15 plus 1 times 6. That's kind of how I like to write it, just because if I have to do the next one, if I have to do the next iteration, I just make that 2, right? That's all it is. But it's 1 right now. It's I is 1. Put a 1 there. And then we do mod 11. So 15 plus 6 is 21. Mod 11 is 10. Right? 10 is also taken, right? That's the thing. So 10 is also taken. So what we're going to do is we have to now do like what I just said, right? Is k equals 15, I equals 2, h of ki is equal to, and I'm just going to, again, I don't have to do the whole big calculation again. Don't know what that is. I just switch that to a 2. Just a little simpler to do that. How did I come with hki from the given h of k equation? Well, this is what was given to us. That's the definition of double hashing. That's what was given to us. So I just put k in there, and I put in 1 plus k mod n in there. Right? Does that make sense, Prasraj? Yeah, okay. So carrying on, 15 plus 12 is 27. 27 mod 11 is 5. So 5 is free, right? Is 5. 5 is good. So we can put 15 into the 5th slot. Okay, there we go. So it actually ended up being the next slot again. Is that what I put for my answer? Oh, that doesn't make sense. Hold on. 27 mod. Wait a second. I got a different answer when I did this before. That doesn't seem right. 15 mod 10, yeah, is 5 plus 1 is 6. 15 plus 6 is 21, which is 10 mod 11. 10 is taken. So I do times 2. 15 plus 2 is 15 plus 12 is 27. 27 mod 11 is 5. Okay, maybe I did it wrong before then. Because I got in the 6th slot before. But 27 mod 11 is not 6. And I do remember saying 27 when I was doing this before. So I think that's fine, honestly. Anybody, hopefully, if there's anybody in the chat, yeah, got 5th slot too? Okay, good. So now I think I did it wrong before then. Anyways, it's fine. So, yep, we go into the 5th slot. And we're done with 15. So now this yellow section is not the same anymore for the next one, right? So for the next one, we have 28. We do 28 plus 0. Remember, 0 attempts with 28 so far, so it's fine. 28 mod 11 is 6. So that's fine. I can put 28 here. Then 17 plus 0 mod 11 is 6. Not good, right? So k equal to 17, I equal to 0, h of ki equal to 6. This is taken. Right? Let me just separate this out. This is for 17. This is for 15. So then what I have is that hki, so for my next attempt, right, I equal to 1, hki is going to be, if I remember correctly, I already don't, is going to be 17 plus 1 times 17 plus, no, 17, no, 1 plus, yeah, there's a lot of, 1 plus 17 mod 10. Close, close, close. 3 close brackets? Yeah. There you go. Mod 11. Okay, long formula. Yeah, is there a question? No? Good? Okay. I think someone has their mic on. I can't see who. Okay, there we go. Okay, so next, we do this for I equal to 1. So then we have, okay, so again, this whole part is the same. So 17 mod 10 is 7, plus 1 is 8. So it's 17 plus 1 times 8, right? Mod 11. So that's 25 mod 11. 25 mod 11 is 3. That's fine. That's not taken, right? Yeah, perfect. So 17 goes here. Now, 88. 88 mod 11, right? If I just go with the formula here, 88 plus 0 mod 11 is 0. Already taken. So 88 now, right? This is with k equal to 88, I equal to 1, right? So HKI equals, so it's going to be 88 plus 1 times 1 plus 88 mod 10. Just using the formula here that was given to us. 88 mod 10 is 8. 8 plus 1 is 9. So this whole thing is just going to be 9 mod 11. 88 plus 9 is going to be 97. 97? Yeah, 97. 97 mod 11 is going to be 9. There you go. Is 9 already taken? 9's already taken. So we set I equal to 2. HKI equals 88 plus 2 times 9 mod 11. I can't do this in my head. So 88 plus 18 is 106. 106 mod 11, right, is 9 times 11 is 7. And if 7's taken, 7's not taken. So we can put 88 there. 88 there. Perfect. And then 59 mod 11 is, what did we say was 4? 4 is already taken. So 59, it's the last one. I know it's kind of a long question again. K equal to, K is equal to 59. I is equal to 1. HKI is equal to, and then here we have, what was it? Oh yeah, HK is, so it's going to be 59 plus 1 times 1 plus 59 mod 10, right? Close bracket, mod 11. So 59 mod 10 is 9, plus 1 is 10, so it's 59 plus 1 times 10 mod 11, right? So 69 mod 11 is 3. Is this taken? It is. Okay, so we got to go to I equals 2. This is going to be 59 plus 2 times 10 mod 11. Right? So it's going to be 79. 79 mod 11 is 2. 2 is not taken. So 59 can go there. There we go. That sounds right to me. So, okay, let's take a look at the chat. Lots of questions in the chat. I got 3 for the remainder. So is double hashing mainly to not make a linked list like in the hash table? All of probing is to not do a linked list, right? All of probing. That's the whole point. Double hashing is one way to do probing. Linear probing and quadratic probing are other ways. That's one of the ways to handle collision. Open addressing. No calculators for the exam. I don't remember anything about calculators. I'm gonna be honest. I don't remember. I don't remember what he said. All problem solving techniques are done. All probing techniques are done because we assume a constant constraint that each key of our hash function can only contain one item. So yes, even linear probing. Yeah. I did a hashing question on the exam. I had to make a linked list for one thing is table. Is that linear? So linked list is, yeah, linked list is not probing, right? So those are two separate ways of handling collisions. Wow, the camera's way overexposed for some reason. I just realized. Open addressing is probing, close addressing linked list. Do you go over? Yes, we did go over linear probing already. That was the first kind of probing. That was the first kind of probing where you just go to the right to find the next open slot. That's all it is. So I realize I'm going a little fast. It's because we are on the first two things and we're most of the way, we're well past halfway. I think it's time for red-black trees. Does that sound good for everybody? It's time for red-black trees? Yeah? Okay. Yep. Okay. So I'll move on. I'm happy to answer any other questions there about probing and stuff like that. But let's move on to red-black trees. So red-black trees are something that I still have to memorize. So I haven't fully memorized. I've memorized insertion, but deletion I have not fully memorized. But I'd highly recommend my notes for them because I tried my best to write them out in a concise way. I'd highly recommend this video if you're confused about red-black tree deletion. Someone posted in the chat just a little bit ago is Jenny's video. I can post it here too. Jenny's just this YouTuber. Jenny's lectures. I'll post it in the chat here. I don't know if I'm allowed to, but yeah, there you go. So highly recommend that for deletion. It's very, very helpful. I'll also put it in here. So I'll say recommend for deletion. There's a video here. Oh, can't paste it for some reason. No, doesn't let me. No, still. Okay, it doesn't want me to paste it. I don't know why. There must be something better than OneNote. Deletion, the slides in Resonansky for, like you said, there'll be case 3 for like deletion. Yeah, so the case 3 for red-black tree deletion will be given to us on the exam, like the how to do it. But I'm gonna be honest, I don't exactly follow his way of doing it, and we get the same answer. It's the same process, but like the wording and the numbering of the cases is different than how I do it, but it's the same thing. You're still making a red-black tree. So let's go ahead and look at some examples I have. Yeah, I don't like the wording and numbering of his cases. Exactly. So that's why I don't follow it at all. It doesn't make any sense to me the way he worded and followed it, worded and numbered it. Red-black trees. So we're going to start with insert the following numbers into a red-black tree, right? We're just going to insert these numbers one by one. So remember, a red-black tree is a binary search tree. So by doing this, we're also going to be practicing binary search trees. So let's begin. The first rule of inserting elements into a red-black tree is that you insert them as reds. Let me actually just get my actual notes here. Red-black trees, insertion. So here's our steps. They're not super concise because there's one thing in it that's like doesn't explain exactly how to do the rotations, but here's the steps. If the tree is empty, create a new black node and set it as the root. So there we go. That's an important thing, right? So tree is empty right now. So we're going to create a new black node and set it as the root. Now, if the tree is not empty, create a new red node and insert it just like a BST. So I would insert 4 here. Right? Nothing wrong. So remember the properties of a red-black tree is that the two that really matter is that every red node has to have 2 black children, and then every path from the root to the leaves has to have the same number of black nodes. So those are the 2 important things, but I won't write those down. So 5, and I inserted 4. Now I'll insert 12. Nothing wrong yet, right? I'm just going to insert 12 here, right? Remember, whenever you insert it, it's red. So next I'm going to insert 2. So 2 would go here, right? And now we have an issue, right? We have a double red. So when you're doing insertion, the thing that can go wrong is double red. When you're doing deletion, the thing that can go wrong is double black, right? That's kind of how we think about it. So insertion, you're going to get a double red sometimes. You're going to have a red and a red. It violates the property that every red node has to have 2 black children. That's not true here, right? So at this point, it's really just remembering the cases, right? So if the parent of the new node is black, insertion is done. If the parent of the new node is red, then if the uncle of the new node is red, then recolor, okay? So what specific recoloring we do, so that is the case here, right? Because this is the newly inserted node, and the uncle of it, which is 12, is red. So we recolor. But what does that mean, right? What that means is we switch 4 and 12 to black, right? 4 and 12, we make them black. 4 and 12, we make them black. And then we also switch the color of the top node. but the root node always has to be black, so this switches back to black now. Okay, but in general, you switch the color of the parent, right? So this would be the parent, this would be the uncle, and this would be the grandparent. You switch all the colors, but another important thing is that immediately, whenever possible, you recolor the root back to black. If it ever turns it out red in any of your algorithm, in any of your cases, immediately turn it black again, right? So like that's what we have here. So this is what it is after this time. Question? No? Good? Ethan, you gonna say something or no?
Oh, so sorry. I didn't realize my mic was on.
Okay, no problem, no problem. A black node can have 2 black nodes. That's fine. Yeah, there's no restriction on black nodes, right? There's no restriction on black nodes. There's a restriction on red nodes. Red nodes have to have 2 black children. Okay. So yeah, these 3, which is actually. Can we choose any number to set as the root, or does that have to be the first one? If he says insert it in this order, you have to do it in the order. Otherwise, it's fine. Yeah, doesn't really matter. But in the I'm assuming in this order. Yeah. Okay, let's continue. So next, we inserted 5, 4, 12, 2. Next is 3. So 3 here, here, and it's here, right? So 3 would be inserted here, right? Okay. Here, that is right. That is correct. Yeah. So we have an issue. Again, the parent of the new node is red, which means we have a double red. If the uncle of the new node is red, the uncle is not red. Remember, every node has like a little baby, little black node here, right? So we have these, the uncle of the newly inserted red node is black. And so we don't have this case. And so my steps here are a little bit vague. It says, if the uncle of the new node is black or nil, then do suitable rotations and recolorings. So let me be more specific now about what I mean by this. You have to identify what orientation the double red is in. So I'd call this line an R line because it's to the right, and I'd call this one an L line. And so what we say is this is an LR formation, right? This might be a dumb question, but why can't you connect 3 to 4? 3 to.
Sorry, I meant 4 to 3. Like you can connect the 3 to the 4th node.
Like this right here?
Yeah, like that.
Yeah. Well, everything to the right of 4 has to be bigger than 4.
Oh no. Okay.
Right?
Can be.
Makes
Okay.
sense?
Less
It's a binary search tree, right? So 3 is less than 4.
Yeah. Almost forgot.
Yeah. No problem. So you have to understand the formations to know how to deal with this situation. So you have an LR formation. You could also have an RL formation. You could also have an LL formation, or you can have an RR formation. And hopefully you can assume what that looks like, right? LR, LR, RL, RL, right? LL, LL, right? RR, RR, kind of looks like that. And so what we do is we turn LR into LL, we turn RL into RR, and we turn both of these into a red-black tree. So it's not, it's not a red-black tree right now because there's a violation, right? But this is kind of the way we do it for insertion. If you have an LR formation, you turn into LL. If you have an RL formation, you turn to RR. And then if you already have an LL or RR, you just turn that into a red-black tree, right? So maybe you land like this. Maybe this is how it gets inserted, and you just go right to the red-black tree. So now let me explain how we do this, right? So to go from LR, which is what we have right now, LR, to LL, what we want to do is we want to left rotate on 2. Left rotate on 2. So those nodes are going to shift to the left, right? Now let me draw the left rotation clearly here. So this is probably a good way to see a left rotation, right? So left rotate means this node moves left. This node also moves left. Everything's moving left this whole time, right? So there you go. There's your left rotation. It was pretty simple because these nodes didn't have any children. Sometimes left rotations can be more tricky. I'll show you maybe an example of left rotation later on. So you see how we left rotated, and now we're in the LL formation, right? Now, what we want to do, now that we're in LL, we want to, so let me write this here. To go from here, we left rotate, rotate parent, right? To go from this way, we right rotate grandparent, right? Right rotate grandparent. This would be the grandparent, and we want to right rotate the grandparent. Importantly, keep the coloring the same. Unless I say otherwise, keep the coloring. Like the coloring moves with it. The coloring moves with the nodes, right? So right rotating this would look like 4 moves to the right, right? 3 moves to the right, and 2 moves to the right. But it looks like we're not done, right? Looks like we have something's up, right? Like this is still not a red-black tree, right? But what you want now is you recolor. So there's plus recolor. Recolor is a separate operation. Plus recolor into black. Am I remembering it right? Black, red, red. Black, red, red. Yeah. Okay. Doesn't matter what they are right now. You want this triangle to be black, red, red. So I'm going to make that happen. Right? Black, red, red. There we go. And now it should be a red, black tree. 1, 2, 1, 2, 1, 2. Yeah, there we go. We're good. So the recolor operation is separate from the rotate. For some reason, he likes in the lecture, they were like the same operation. They're not the same operation. Right rotating has nothing to do with color. The colors move with the nodes. But then you do a recoloring. You recolor it to be black, red, red. And there's the mirror case here, right? Where if it was RL, you would right rotate parent. And then here you would left rotate grandparent and recolor the triangle to also be plus recolor, right? Black, red, red to also be black, red. Technically, can you not do red, black, black? Black, black. That would be fine. That would be fine, but this is the algorithm. Maybe it screws up something lower down the tree. It probably doesn't. I don't see why it would screw up anything lower down the tree. Yeah. But what if this node was red, right? If this node was red, then you might be propagating the problem up more. This doesn't let that problem happen, right? So there's that. In this case, it would be the same thing. So what we see right now is the tree is being right rotated. Well, there was a couple things. We started LR, right? Then we left rotated to get LL. Then we right rotated grandparent and recolored, right? A lot happening in that step. Let me recap it, right? So this is our final product after this, but to begin with, it looked like 5, remember now, 4, 12, and then it was a 2. Was it a 2? I think it was a 2. Yeah, a 2. Yeah, 5, 4, 12, and 2. And then we had a 3, right? Okay, so this is what happens right after you insert 3. So right after, 3 is put in. So we'd have a double red, and the uncle is black here. It's a black node here, right? So I can't just recolor. I have to do some rotations. This is LR. This is LR formation, left then right. What I want to do is I turn LR into LL. How you think about it? You're just swinging this so it's a straight line, right? You want to swing it straight. So what we're going to do is we're going to kind of like swing that open, and what it kind of looks like by doing that is we left rotate. So left rotating the parent looks like this, right? That's left rotating the parent. Everything moves left. Now it's LL. Then, this is not right after 3 anymore. Then I'm going to right rotate the grandparent, right? And recolor. But let's just start with the right rotate. Right rotate the grandparent means this, right, moves down. 3 moves up. 2 moves up. Everything's moving right though, right? Everything's moving right. So again, if you just look at it like this and you don't do anything else, nothing's been fixed. We still have a double red. Right? Still have a double red. But now you recolor. You additionally, separate operation, recolor. You want it to be black, red, red. Right? You want it to be black, red, red. So black, red, red. And there we go. That's our operation. Yeah, if that matches this, left rotate, right rotate, right rotate, left rotate, right rotate, left rotate. Yeah, it's just the LL and RR also have a recoloring there too. They also have recolor. You also have to recolor into black, red, red. So the LL and RR have a recoloring. But yeah, otherwise that looks correct. And remember which node you're rotating, because here's the parent, here's the grandparent. Right. But it's a lot to memorize. But if you just think about it, like, you know, if it's like this, you want to turn it into this, right? And there's a mirror case, obviously, right? You want to turn it into this, and then you want to turn it into a tree, right? So you're kind of turning this, turns into this, turns into this. The point is you're trying to make a tree, and you're doing it by a left or a right. In that case, it's a right rotate and then a left rotate, right? Okay, let's keep going. I don't have to insert all these nodes. This is going to take a little while, but maybe I'll do a couple more just because it's good to see insertion. So 7 would be next. Remember, you always insert as read. So 7 is bigger than 5. 7 is smaller than 12. So 7 goes here. Nothing else happening there. Okay. Next, we have 7 again. So bigger, smaller, and then you always say smaller. Like if it's the same, you just say smaller. So we have a double red, and the uncle is black, right? The uncle is black here. This is a good example because now look, we don't have a LR or RL situation. We have an LL situation, right? LL. So to solve the LL, we right rotate grandparent. So 12 is right rotated. So right rotating 12 would look like this. I take 12, move it down to the right, take 7, move it up, take 7, move it up, but it's all moving to the right, right? Once again, nothing's fixed until we recolor. So I also have to recolor it into black, red, red. That's important. Black, red, red. And there we go. Now it is fixed. Less than equal to. Less than equal to. Yeah.
Hey, can I ask a quick question again?
Yes, of course.
There's the two values here, 7 at the black note 7 and the red note 7. They're both the same value, right? So
yeah,
it doesn't matter how you switch them, because if they're the same, like when you do right rotate, and like you have to make sure that it follows binary search tree rules, right?
Yeah.
So like the right side has to be greater, and then but this one than the left side.
Yeah. So if the number is the same, you just go left. You just go left.
Okay.
It's kind of just a general rule.
In this case, it really doesn't matter. It's just you're still safe either way when you right rotate.
Exactly. So the right rotating and the left rotating will never mess up the binary search tree. Left rotating and right rotating, that'll never mess up binary search tree. Right? So that's it. Yeah. And the recoloring, of course, will not mess up the binary search tree because it's just recoloring. Okay, so there we go. That's 7.
Wait,
7
can I ask
again.
a question?
Yes, of course.
So you know how you said that the left rotate and right rotate doesn't change up, like it's still a binary search tree.
Yeah.
Does that mean that there's more than one correct binary search tree?
There's yeah, for sure. Yeah.
Okay,
There's more than that's actually kind of the whole point of red black trees, right? Because there's lots of ways to make a binary search tree. You could make a binary search tree that's like, 4, 5, 6, 7, 8, right? But this isn't a good binary search tree because the height is too big. Right?
Yeah.
The height is too big. We want it to be balanced. We would prefer it if we wrote it like 6, 7, 8, 5, 4. This is better, right? Because the height is smaller.
Yeah.
Right? And that's the whole point of red black trees, is that we want to convert a tree that looks like this into a tree that looks like this.
Yeah. Okay.
Right?
Thank you.
Okay. No problem. Okay, so there we go. So that's 7, 7, and then we have 9. 9 is the next one here. I guess we'll finish it. Well, how much time do we have? Like half an hour left. I'll get to deletion after this. Don't worry. I know deletion is the main thing that worries me too. So let's get through it. So 9 is next. So 9 is bigger than 5, bigger than 7, smaller than 12. So we have a 9 here. But this time we have the uncle's red. So since the uncle's red, you just recolor these nodes. You just recolor these nodes to black. You're done. I think. 1, 2, 3, 1, 2, 3, 1, 2, 3. Yep, you're done. There you go. I want to make sure.
Hold on, shouldn't we? Don't we need to recolor?
Recolor 7. Yes, I always forget to recolor 7. Sorry. Always forget to recolor 7 for some reason. There you go. So now it's 1, 2, 1, 2, 1, 2. Yeah, there you go. It's good. Yeah. I don't know why I always forget to recolor 7. I don't know. You recolor these two nodes and you recolor the grandparent as well. I swear I'm going to make that mistake on the test and I'm going to lose marks for it, but we'll see. So inserting 6, 6 is bigger than 5, smaller than 7, smaller than 7. So we just put a 6 here. No issue, right? Inserting 6 again, we have same, it's going to go right here, right? So you go left for the 6. Now we have LL again. Okay, it'd be nice if I, how about we make it, 8, 8? I'm make this 8, 8 instead. It's just going to make it so it's not so repetitive. We make it 8, 8 instead there. So if it was 8, 8, then we would put an 8 like this and an 8 like this, right? Now I have an RR orientation. RR, we left rotate grandparent and recolor. So we're going to left rotate the grandparent, 7. Yeah, you're right, actually. Oops. I'll make it 9 then at the end here. No, that doesn't make sense. Can't make it 9. No, why did I even do that? Sorry, that's wrong to put. That's wrong. Okay, you know what? Then I can't change the example. Never mind then. It's the same thing, the reverse case. You just rotate the other way. Here we have 6, 6, right? Uncle is black. So what we want to do is we want to right rotate the grandparent. Right rotating the grandparent would look like this. So the 7 moves down to the right, the 6 moves up to the right, and the 6 moves up to the right. Again, we have to also recolor. So we want it to be black, red, red. And now that's a binary search tree. Well, I mean, that's a red black tree. 1, 2, 1, 2, 1, 2. Yeah, good. Perfect. Okay, good. So there we go. I inserted all those numbers. I wanted to do an example where I get suggestions from you from the chat, like from different numbers, but we're running out of time. So let's move on to deletion. But before I do this, I want to just show you, first of all, this is a good copy of the tree, but also there's a really good resource for binary search trees. I keep saying the wrong thing, for red black trees. It's like a visualizer, right? So if you look here, I can insert these nodes. I have it written on my screen up here, so I can show you there, right? So we can insert like 5, right? And it'll play an animation of what it means to insert, right? Insert 5, 12. It'll do what I'm doing here. 12. I'm not gonna do all of them. 12, 2, right? And then it shows the recoloring, right? 3, and then I'll do one of the 7s, or maybe I'll do both 7s. So you see there's a rotation that has to happen, another rotation has to happen, and a recoloring, right? 7, and then I'll do one more 7. 7, and you can see the animation that plays, right? So it's gonna be this, and then it's gonna do 2 rotations, and it's gonna do the recoloring there for you, right? Yes. I'll send a link for sure. Send a link in the chat right now, and I'll put it in the document if it lets me. It does not, so I'll. Can I just paste like that? No. No Shift V. Not letting. Oh, Sim put 7 on the right of 7. Okay, yeah. It doesn't change anything. In fact, we have the same binary, like the same red black tree at the end, right? Probably the simulator's right and not me, so I guess you go right, but I don't think it matters because it's the same number. So the property is still held because it's equal to for both cases. Anyways, yeah, there's that. Let's just see. Yeah. Okay. So let's move on to deletion. Moving on to deletion. Oh, I shouldn't have closed the chat. Let's move on to deletion here. It does, the simulator does deletion as well, by the way. So what we want to do is we want to take nodes from this tree. I'm just going to use this tree here, and delete nodes in some order, right? So delete. Let's delete 2. Right, delete 2. Oh, let me show you the cases for deletion. So the cases for deletion are more complicated. So the first 2 cases for deletion are okay. So there's the way I wrote it in my notes, there's 6 cases in total, right? Yeah, I'll delete the root. Sure. So here's the first 5 cases, and here's the 6th case. Really, I think what I'm gonna do is I'm just going to generate a bunch of random red black trees, over today and tomorrow, and I'm going to one by one delete all the nodes in a random order. And I'm going to do this just a bunch of times, and hopefully that will make me memorize the cases, and then I can do it without looking at the cases. That's kind of my plan. At the moment, I still have to look at the cases, so that's kind of my main thing for today and tomorrow, is to just do this so that I remember. And then, well, yeah, you'll see it. We don't have to memorize deletion, case deletion. Yeah, you're right. You're absolutely right. There is no, like, it'll be given, like, what's called case 3 of deletion will be given. I don't like the way he words it, though. So it's a little bit like, yeah, it's like, I don't really even look at his slide really for it. It's the third of his cases. His wording and the numbering, I don't really like it. So it's given in his wording, so it would be hard to understand the exam. I think so. So they're not actually different. They're just numbered differently. They're numbered differently. And what the way we name the nodes is slightly different, right? Yeah, screenshot my steps here like this. So yeah, I just don't really particularly like. They're not, again, it's not different. Like, it is actually the same thing, but the way it's phrased and the way we number it and the way we word it is different, and I much prefer this way. Oh, like this? There you go. Right? You'll need to follow his numbering if it asks on the exam. Yeah, so I would recommend looking at exactly what his numbering is, but what I would honestly recommend is look at his numbering and compare it to what my numbering is. Maybe I'll add that to the note tonight. Okay, I'll add that to the note tonight, how it compares, because, oh, I just realized that's this. Oh, never mind. Sorry. I thought I made a mistake in the typing. It's just big like that. There you go. Maybe I'll add that to the note tonight, is like how it compares to my number, because that is important. So yeah, if you want, I made the diagram for red black trees based off of Rezo's slides. Let's see what the diagram is. Oh, Jasper. Hi. Okay, yeah, great. Perfect. Okay, so Jasper seems to, Jasper, of course, writes very nice notes as well for this course. Yeah, apparently his notes are, I remade the diagrams if you want to base it off Rezo's slides. There you go. That's a good option too. I'll also add to my notes how it compares, but Jasper's notes are a very good resource as well. Thank you for sharing that, Jasper. So let's go ahead and do deletion. So delete 2. Right? Delete 2 is a very simple case. Delete 2 is you're deleting a red node with no children, right? So if the node to be deleted is red, then just delete it as in step 1. So deleting Z as in a binary search tree. So you essentially just replace, like, you just delete it. That's it. If it's a red node with no red children, then you just delete it. Sorry, with no children, you just delete it. It doesn't affect the black height, right? It doesn't affect the black height at all. So remember, with deletion, the thing that can be affected is the black height, right? But that doesn't affect it here. So that was an easy one, right? Same thing with 4, right? Same thing with 7 and 6 and 9. These would all be the same. Okay, let's delete. What's a good one to delete? I don't know. Let's delete 12. I don't know. I didn't really make a list. I didn't really make an order. So that was delete 2. Now let's delete 12. So deleting 12, what you do is you replace it. Deleting 12. Oh, this is a weird one to delete. Deleting 12, you replace it with the successor. The successor of 12, there is no successor of 12. So you replace with 9 and delete 9. Yeah, that makes sense. So you have to replace it with the predecessor. So what I'm going to do is I'm going to, take away the 12, put 9 here, and delete 9. But deleting 9 is no problem, right? Deleting 9 is no problem. So then we just have a 9 there. That's it. Notice the color of the position stays unless I say otherwise, right? The color of the position stays there. So let me redo delete 12 there, right? Yeah, that makes sense how I did that, right? I think we don't have to recolor. No, I don't think we have to recolor. So deleting 12 with the predecessor, right? I'm just going to, a better way to say it is I'm removing 12, I'm replacing it with its predecessor, which is 9. And then I'm deleting 9. Deleting 9 is the same thing as like we just deleted 2. You just delete it, right? And then we're done. The black height should be correct still. 1, 2, 1, 2, 1, 2. Yeah, the black height is fine. Importantly, right? The color of the node stays. Again, unless I say otherwise, the color of the node stays. So you only replace the number inside. You're not actually removing the actual node, the circle, so the color is preserved. Exactly. We're not like getting rid of the circle. We're just replacing the number. even in this case here, when we have a 9, we had a red 9 here that we're deleting. What we're really doing, right, is we're replacing it with its predecessor, which is the nil node, right? So it's becoming the nil node, and the nil as part of a red-black tree has to be black, right? So we just have 2 black. How do I count black height? Yeah, so how I'm counting black height is I just go 1, 2, right? So you don't count the root and you count the leaves, like the absolute leaves, the nil nodes at the end, right? So I go 1, 2, 1, 2. I didn't draw them, but there's nil nodes here, right? And 1, 2. That's how I'm counting the black height. Does that make sense how I'm doing that? Again, there's nil nodes at the end here that I just haven't drawn. There you go. Okay, good. Deleting 12. That's it for deleting 12, right? Again, you replace it with either its successor or its predecessor. I usually go with successor, but you can also do predecessor. And from there, you preserve the color in the spot, and you delete that node that you're replacing. And then that's a whole separate delete case. That could be a different case entirely, right? Yeah, okay. So, okay, do we go over how to delete from binary search tree, or we only learned that for a red-black tree? Yeah, I didn't have time to go over binary search trees, right? But it's actually the same thing, right? It's pretty much the same thing here, right? So when I delete, like, that was 12. Let's delete, I don't know. Let's delete 9 next, right? Let's see what that is. Okay, that's not going to be same like deleting from a, what's it called, a binary search tree, but we'll see in a second. The distance to the nil always has to be the same on each branch. Yeah, that's a property of red-black trees. So delete 9. All right, now we have, this is going to be a complicated one. What we do is, first of all, we replace it with its successor, right? So the successor of 9 is going to be, no, we don't replace it with successor. We delete 9 and replace it with, we replace it with successor, which is nil. And so it's going to be a double black, because a black nil node goes in there and it's already black. So it's double black now, right? It is a double black nil node here. There we go. There's our first double black situation. If now step 2 is handle double black, right? There we go. So let's figure out what's happening. So if the node to be deleted is red, then just delete it. If the root is double black, then just replace it with black. Not the case. If double black's sibling is black with 2 black children, no, it's not that. So the sibling is not black with 2 black children, it's black with 2 red children. If double black sibling is red, no. If double black sibling is black with the far child being black and the near child being red. So double black sibling has a far child and a near child. So this case is the far child is black and the near child is red. That's not the case. If double black sibling is black with the far child being red. Yes, that is the case. Double black sibling is black with the far child being red. So it's case 6 here. Yeah. I'll explain it in this case too. Yeah, so yeah. So swap the color of double black's parent and double black's sibling, right? So swap the color of double black's parent and double black's sibling. So double black's parent becomes black and double black's sibling becomes red. Okay. Rotate double black's parent towards double black, right? Rotate double black's parent towards double black. So double black's parent is rotating towards double black. So what that'll look like is we move down like this, 7 moves down, 6 moves up, 6 moves up, and very importantly here, 7 moves up, but where's 7 going to go? 7 is going to attach to 7 over here, right? 7 is going to attach to the other 7. It goes, so the important thing is that when you do rotations like that, what I like to call the middle child, the middle children here, right? The middle child there switches to the other one. Let me actually show the picture of rotations, because rotations can be very confusing. Where's rotations? Is rotations, right? So this is what I just did. We have a left rotate and right rotate. Notice when I take the this graph and I right rotate y, b, beta, which just represents a whole other tree, switches to y. See, b used to be attached to x, but now it switches to y. And if you go the other way, b used to be on y, and then it switches to x. right? So that middle child, I like to call this the middle child, switches to the other node. But the outer children stay in the same spot. That's it. So I just did that here. Replace double black with black, so it just becomes a regular nil node here. That's the next step. And change color of siblings red child to black. So the siblings red child was the 6 here. There we go. So 1, 2, 1, 2, 1, 2, 1, 2. Yeah, there we go. So let me play that one again. let me play that one again. So I'll just show this diagram here. Yeah. Okay, that's good. So yeah, let me try to play this again, but OneNote might not let me. Okay, I think OneNote's going to be annoying, so let's just keep deleting. There'll be lots more cases. We're going to do that case again. So let's go ahead and do the next one. Let's try to delete 6. How about that? Let me make this a little nicer, just a little nicer to look at, right? So that should be oh, I lost what was there. 7, black 7, red 7. So a black 7 and a red 7. Okay, let's delete the black 6. Black 6. Okay. So the black 6, deleting this, right? Let's take a look at what this is. Deleting this becomes a nil node, but a double black nil node. Okay. The double black nil node, because the successor right there, right, is going to be like the child is going to be a black node there. So it becomes a double black nil node. Yeah, pretty sure. Okay, hopefully that's good. Yeah. Then we look at what case we're in. So someone says case 5. Let's see. If the double black sibling is black, right, it'll delete the red on. Yeah, that's true. That's true, but I'm just going to specify that I'm deleting the black 6 here. Like, let's say I'd say node 1, 2, 0, 1, 2, 3. Well, I guess you can't really specify it with the array, but let's pretend I'm specifying it with the array. Yeah. That is just that one. So delete, I'll specify here, just to be super clear, the black 6. So we have our nil node, right? Double black's sibling is black, with the far child being black and the near child being red. That is what we have. Okay, swap the color of sibling with red child. With red child. So this becomes a red 7, and this becomes a black 7, right? Rotate sibling away from double black. So rotate sibling away from double black. So that means we rotate 7 to the right. So what that's going to look like is we're going to move this 7 down, right? We're going to move this 7 down. It goes there. We're going to move this 7 up. There we go. And yeah, okay, and there we go. And that's not done yet, right? Now we apply case 6. So that's the thing. We right away apply case 6, which is double black sibling is black, yep, with the far child being red. That's correct. So we do this again. Swap the color of double black's parent and double black's sibling. Double black's parent is going to be a black 6, and this is going to be a red 7. Rotate double black's parent towards double black. So rotate double black's parent towards double black, like this, okay? So then we have the double black nil is going to move down. The black 6 is going to move down. 7 is going to move up. 7 is going to move up. There we go. Right? Then replace double black with black. So it just becomes a nil node here. Change the color of siblings red child to black. There we go. So so it's 1, 2, 1, 2, 1, 2, 1, 2. Yep, we're good with the black height. And there we go. We've successfully deleted 6 there. So we won't be given all these cases in the exam. That's why I'd recommend doing a lot of practice of this to try to remember. Now, you are given case 3 of deletion in his wording, right? Not in this wording, but in his wording, which is probably somewhat helpful. But I don't particularly understand the way he wrote it. Probably I could figure it out on the exam, but I would prefer not to. So yeah.
Sorry, by case 3, did anybody catch like which one he said, or was it just generally case 3? Because there's 6.
Yeah, sorry. This is the numbering
This
here.
case 3 is double black, right?
Yeah, my numbering here is not the same as his numbering, right?
Oh, okay.
So go to his slides and look at case 3. Case 3 has 3 subcases: 3A, 3B,
Yeah,
3C. That's going to be given to you.
Yeah, I'm looking at the slides right now, and then there's case 3 mirrored.
Yeah. So it's case 3A.
He didn't specify which one.
Yeah, he let me show you. He specified here. If you go to the discussion board for the course, communication discussions, you go to answers. You just put, do we need a calculator? If I ask you to type a question that needs some calculations, the numbers will be small enough without needing a calculator. Okay, good. The following note will be provided. There we go. This will be provided.
Okay, let me go look for that. Thank you.
Right, that's there. Okay, no problem. Okay. So let's move on. So deleting 6, I don't know. What should we delete next? Delete the root. Let's delete the root. Right? Delete 5 is the next one. Right? So deleting 5, we replace it with its successor. So 6 goes here and we delete 6, right? So we replace it with, so 6 is the successor, right? So we replace it with its successor and then we delete 6. So deleting 6 would turn it into a double black nil node. And let's see what happens. So if double black sibling is black with 2 black children, that is what we have, right? Double black sibling is black with 2 black children. Then we remove double black by replacing it with black. Add black to the parent's color. So add it. So red. So there's like a little bit of an arithmetic here kind of, but red plus black is black. Black plus black is double black. And then if you try any other combination, it's nothing, right? So red plus black is going to be black, right? And then make sibling red. So we have a red sibling. And there we go. So we deleted the root there, like that. Okay, well, what do you guys think? Do you want to? I'm fine going for, yeah. What was the last case? What was the last one? Oh, so we have to memorize insertion. We definitely have to memorize insertion, but insertion isn't that crazy to memorize. What case was the last one? The last step was case 3. For my case 3, that was that last step, case 3.
So wait, so for your numbering for case 3, case 3 has 3 subcases. So case 4, 5, and 6 are like the subcases for case 3, according to your number.
I don't know if that's true. I don't know for sure. I'm gonna go over it tonight, and I'm gonna add that in the notes here. Yeah, okay. If Parthivash says yes, it's true, so maybe that is true there.
All right.
Yeah. Okay.
Wait, so wait, I just want to confirm your case 4, 5, and 6 are his case 3.
I can't personally confirm that. I'll look at that tonight. But I think Parthivash says yes, it's true. So
okay, all right.
Yeah, there you go. Okay, so what do you guys think? Do you want to do a little bit more red-black trees for 10 more minutes, or do you want to do a graph question?
Can we do a graph question? I want to know how we should draw it out for like the BS team.
Yeah, like BFS and DFS?
Yeah. Like, are we supposed to, like, the way Jenny does it versus how he does it in the lectures?
Okay, let's. Shouldn't the red 7 be on the left side of the black 7? Isn't it left side for less than equal to? Yeah, but if it already was there, like from the rotations, it's fine. What I mean when I was saying you go left, apparently you actually go right. I think it doesn't matter. It's just like if you have to make a decision, but like we didn't have to make a decision where the 7 goes here, right? So the 7 just goes where it ends up after the rotations. Okay, so let's try a couple graph questions for a little bit longer here. So let's see what time it is. Yeah, so let's go. Okay, let's do this graph. Let's do DFS and BFS on. Let's start with BFS, right? BFS on this. Right, so BFS. So doing BFS on this means breadth first search. Breadth first search as in like, you visit all the children before you go to the grandchildren. And we're going to assume alphabetical order. So from A, right, we visit B. This is the next node you can visit, right? And then from, you go back, you visit any other children, right, that haven't already been discovered, right? So what you would do, let me make sure I'm doing this right. BFS. Yeah, that haven't already been visited. So there's a difference between visited and discovered. So there's unvisited, right? Discovered and visited, right? So you move up the hierarchy here, right? So to begin with, everything's unvisited except the source, which you start with, right? Which is visited, fully visited, right? And then you discover all the other nodes here, right? And you visit them one by one. So you discover all these nodes, right? So you've discovered B, F, and E because those are reachable. Then you move on. Something up with the answer here? Okay, something's up with the answer. Okay, so B is the next alphabetical one that you can visit out of the discovered nodes. Then we have F, which is the next one you can visit, right? And then E, which is the next one you can visit, right? So we've visited all of these nodes and we've discovered now, right, I and C. So you'd next move on to C, right? And then I. And now we have the options of visiting J, M, N, D, G. That's it, right? So just alphabetical order. So go like this, D, G, right? Yeah, looks good. And then J, M, N, right? Yeah, looks good to me. Then we have what we've discovered. What are the options for us now, right? The options for us now for our next run is this node, this node, this node. That's it. Not G, right? I don't highlight G, even though you can get from here to here. It's already been visited, right? So we don't have to visit it again. So from here, right, you would say highlighted are discovered. Yes, highlighted are discovered. So from here, you would go D to H, right? J to K. So then you'd go to J to K, and then you would go G to L. G to L. Yeah, G to L. Now those are all visited, and so now we have discovered. The only two discovered ones are these two, and it doesn't really matter which one. They will both be gone to there. And there's BFS. There's our BFS of that graph there. How do you feel about that? Is that okay?
Can you just go over how the highlighting things again? I don't understand that.
Yeah. So you just start with a node, right? The node in your search is just like the starting node. So you have A, right? That's your starting node. And from A, you can reach B, F, and E, right? So that means they've been discovered. And so now when I start drawing lines, right, that, make some sort of, pathway to search through here, right? We search in this order, right? We go B and then alphabetical order, B, F, and then to E, right?
Okay.
And then from here, we now have more nodes we can discover, right? That we have discovered. I has been discovered because it's now reachable. C has been discovered because it's now reachable.
Yeah.
The rest of them aren't reachable, right? So I don't highlight them.
Right.
So we go here and here, and now we have new nodes that are discovered, right? So discovered, 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 discovered.
So like the source or whatever source, node that you start at, that's where you find your new discoveries? Or like that's where you find like new discovered nodes? So like now
like the furthest level.
Okay. Mm-hmm. So like from here, like now you're at C, your source node, and then you find D, G, and J.
Yeah.
Okay.
J is from I. J is from I, right?
Oh, J is from I. Okay.
Yeah, right. But yeah, there you go. And you go like that.
Okay, so from here, let me try again. So from here, I is your source node, and then you find J, M, and N. Right?
That's actually already done. That was actually already done.
Okay.
That's when I drew these. That's when I drew these green lines here.
Okay.
Yeah.
So what I'm trying to get at here is like the source node kind of changes as you go further down the graph.
Yeah, these are like what I'm going to highlight in green now. These are your source nodes, and those source nodes are discovering H, K, L, and that's it. H, K, and L. Right?
Got it.
And then the switches. So now you just you do it in the right order, right? So you say D to H, what was it? D to H, G to L, J to K.
All right. Thank you.
No problem. No problem. Yeah, there is something I'm supposed to be writing down. BSD first. So it would be easier if you put nodes in a queue after you discover them. Yep, for sure. Do you write down stuff as we go along for BFS? Yeah. You write down the visited nodes. Yeah, I always forget to write down things. Just the visited one. So yeah, it's sort of like the order that you visit them in. So we visited A first, right? And then after that we visited B. And after that we visited E. Right? E would be the next one we visited. Right? Because I went, oh no, sorry. Yeah, E is the next one I visited, alphabetical order. And then F, the next one I visited. And then C, right? C is up here. And I is the next one I visited. Okay. Then D, right? D was right here. Definitely easy to do this as you're going, right? Much easier to do it as you're going instead of all at once. So let me just write it from the beginning, right? So we started A, discovered immediately. I mean, visited immediately. So B is the next one, right? Then F, so then E, then F. Then from B, we go to C, right? And from E, we go to I. Right? Then from C, we go to D, and then to G, right? So G goes here. And then from I, we go to J, and then to M. Right? Then from D, we go to H. Let's move on to the next line. H.
Yeah, you forgot the N, I think.
Oh, I forgot the N? Yeah, I forgot the N. Yep. So from I, we go to N. And then we go from D to H. Yeah, I have to do my alphabet here a little bit. J, K, probably. J to K. Right? And J, K. And then G to L, I guess? Or which one to L? It's G. Which one to L? Which one discovered L? Doesn't really matter. L is the next one though. Yeah, but from where? I don't think it matters. Yeah. G to L? Yeah, G to L makes sense. G to L. And then it doesn't matter which one you put here. I guess it would be O, K to O, and then to P. And there you go. So you see, we visit all the nodes, but we don't visit them. You know, it's not a depth first search. We're not going as far as possible. We're starting, you know, here. You can think of it like we do this layer, and then we do this layer, and then we do, you know, this layer. Yeah, which is F, C, and I. And then we do D, G, J, M. Yeah, we do this layer. That's right? One. Oh no, F shouldn't belong to that. F should belong to this one. F belongs to this one. And then this belongs to this one. Yep. F is pink, yep. I think the pro shows lecture for BFS. Yeah, I have a tree, essentially, right? I have a tree. So from A, you go to B, to E, to F, and then you have other. I have a tree. It's just on top of the graph, right? It's just on top of the graph there. Let me just finish coloring this, right? So 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, and then 1, 2, 3, 4, 1, 2, 4, 1, 2, 3, 4. Yeah. So then this is a different color. This would be your gray section, which would be H, K, and N, and then L, O, and P. L and O would be their own section. So I'll just like highlight it like that. It's getting obviously messy, but just highlight it like this, and then you have that, and P is at the end there. Okay, there you go. This is definitely recorded. Yeah, it's recorded and posted. YouTube's on the bottom of the screen. It says recording on YouTube, Adam Savage. Look up my name. N is blue? Yeah, probably. N is blue, yeah. There you go. So it's just showing you like you do depths like that. You can, of course, draw this as a tree. I mean, I have it as a tree there, but yeah. A to B to C. A to B to E to F. B to C. C to G. G to L, C to D, D to, oh, and L to P, D to H, E to I, to M, to N, to J, to K, to O, and then we said G to L to P. There you go, that's all, right? L is gray, no. O and P is its own color, yeah. Blue, yeah. L is gray, yeah. Sorry, I screwed up the coloring here. And then O and P are their own coloring. Yeah, that makes sense to me. Yeah, should have paid more attention there. Okay. 3 things are coming out of L. Out of L, no. Out of I. Out of I, yeah. Here, here, and here. J, M, and N. Yeah. We'll do a DFS, and then maybe one minimum spanning tree, and that's all we got time for today. Someone just asked, yeah, in public there. Let's do DFS quickly. So DFS of this graph. Let's start again here, right? So let's just for now, let's just start here. So you just go as far as you can in alphabetical order in some direction. So A to B, let's actually just build it. A to B, to C, to D, right? H to H, right? To H, L, that's the only option. L, M, N, O, P. Oh no, G would be first, I guess. Oh no, but yeah, that's fine. No, I would go to P. I would go to P. Yeah. And then there you go. And then I'm stuck here, right? There's that. So then I have here, I just go to another child, right? So I go E to, oh no, I guess I would go, no, sorry. I don't start all the way back there. I go back. I go back to L, right? So I ended here, right? I went all the way as far as I could. I stopped. I go back up now to L. I say, is there anywhere else I can go? Yeah, I can go to G. So L to G. And then G to K, let's say. Or J, I guess, because it's the next alphabetical one. So J, right? J to I. J to I, right? And then it doesn't really matter where we go. Let's go I to E. E to F. And we're stuck because there's nowhere else you can go that hasn't already been visited. So you go back. Anywhere I can go here? No. Go back. Anywhere I can go here? Yeah. M. I to M. M to N. And N to K. And K to O. And we're all visited there. With no respect to order? Yeah, it's alphabetical. So just go for the highest alphabetical version. But that doesn't actually matter. It's just for like to standardize it. I think he asks alphabetical. Just go to the highest alphabetical value. Oh, if you mean left and right on the graph, then yeah, that's fine. Yeah, it doesn't matter. I don't think it matters. I've never heard it matter. So unless someone knows better than me, but I don't think it matters. Okay, guys, let's do one minimum spanning tree. Do you want to do Kruskal or Prim? Prim? Okay. We can do both. It's okay. Do one of each. Let's do this example. For the given graph, let's do Prim on this. Prim. So, Prim, how we do this is we, well, I wrote it out. So, Prim, here's our steps for Prim. Start a random node and discover all adjacent vertices, right? So, okay, so first of all, yeah, and discover all adjacent vertices. Sorry, did I copy something wrong? Yeah, no, that's fine. So, start a node. Let's say we start at A, right? I discover these vertices, right? And I just choose the smallest one. They're the same, right? So I'll just choose this vertex here. right? Then I now have these two vertices discovered or visited. This is discovered, but not visited, right? So now again, I just choose what are the, sorry, I discover all adjacent vertices. Yeah. So then again, all I do is I just choose whatever is the shortest edge, the smallest edge, between that's accessible by these two nodes, right? So either 3, 4, 2, or 2. And importantly, we don't make a loop, right? That's important. We don't make any kind of loop. So I'll choose this 2, right? And then now I do the same thing. I'll just say, you know, out of the edges that are accessible, 3, 4, 2, and 4, I can't choose this 4. I wouldn't because I choose the 2. I just choose the smallest one always, right? There's that. Now, out of these edges, which are, you know, accessible, it's one of these 2 3s. Doesn't matter which one you pick. Choose this one, right? And then once again, it's one of these 2 3s. Doesn't matter which one you pick. We have that. And there's your prim version of this. That would be the same thing, just making sure there's a solution, but I just want to make sure it's the same thing. Yeah, it's the exact same thing. Okay. So there you go. That's your minimum spanning tree, right? So you just keep selecting nodes and you bring a path to the next node. And now you ask, out of all those edges that are accessible from these 2 nodes, what's the smallest one I can take that also doesn't make a loop? And then you add a third node and you say, out of these 3, you know, out of all the edges I can access from these 3 nodes, what's the smallest one that also doesn't make a loop? And you just keep asking that until all the nodes are visited. And then you have that for prim. Let's do Kruskal quickly. Kruskal, you just keep choosing the smallest edges and make sure it doesn't make a loop, right? So is it gonna let me switch colors? There you go. No? There you go. Perfect. So smallest edge here would be 2, right? And then this 2 here would be the next smallest edge. And doesn't make a loop, right? Next is the 3s, right? I'll choose this 3. Then I'll choose this 3. I can't choose this 3 though, right? Because that would make a loop. Then I move on to 4s. I can't choose this 4. Make a loop. Choose this 4. Kruskal, yeah. Did I get the same tree? I got the exact same tree. It doesn't have to be the same tree. There's other trees. Like I could do this, right? There's more than one minimum spanning tree when the edge widths are not unique. Right? The edge weights are not unique. Okay. Yeah, that's right. Okay, so let's do one of either Dijkstra or Bellman Ford. You guys decide which one. Got a Bellman. Got 2 Bellmans. Okay. Looks like, okay. Bellman is with negative widths. Yeah. Okay, let's do a Bellman, and that'll be our last example for today. So here is a Bellman for example. Obviously the prompt is, you know, starting at S, find the shortest path to all the nodes using this order of edges. So they'll give you an order, right? It actually doesn't matter the order, as long as you do all of them and you stick to the order, right? But what we do is we kind of just like make a little table here, right? So let me try to just make it quickly here. It's going to be, you put all the nodes, S, T, X, Y, Z. Actually, I don't need that last one. And then this is distance, and this is predecessor, right? And we just keep updating this table over and over again. It's a little bit big, these words, so a little smaller. Distance and predecessor. Yeah. Yeah, well, we can do, we'll see how it goes. I'm hesitant to say we can do both because I do gotta get going very soon, but we'll see. Let's get this done and then we'll see what happens. Distance. So we just do the order that's stated here, and we just keep relaxing the edges. So T to X, right? First of all the nodes have a weight of infinity, and then 0 from the source. And you just keep comparing, you know, can you relax the edges in the correct order here, right? In the order that's given to you. So T to X, right? I can go from infinity to infinity plus 5. That's nothing. That's not better than infinity, right? T to y still won't be better. T to y, it's infinity to infinity. T to z, infinity to infinity, right? X to t, infinity to infinity. Y to z, it'll all be infinity to infinity until you get to s to t, right? S to t, this edge actually only has a weight of 6, right? Because 0 plus 6 is 6, not infinity. So if you improve the score, you write it down. So t has a distance of 6, right? And it has a predecessor of s, right? Distance of 6 and a predecessor of s. And then you go to the next one, sy, right? Sy, y actually has a value of 7, not infinity, because you can relax the edge. So y has a value of 7 and a predecessor of s. A predecessor is where you go. How do you get to y to get at that score? To get at that score, you have to come from s to get 7. Right? Yeah. So and then now let's go ahead. Let's do it from the beginning, right? Will this be unique? Shortest distance. Yeah, this will be unique. This will be unique. Like maybe I guess I don't know how to prove that, but yeah, this will be unique. So then we have a distance. What am I saying? X to t. X to t, t to x, right? T is 6 plus 5 is 11. That's better than infinity. So I put 11 here, and the predecessor is t, right? Predecessor is t. Let me make these boxes bigger. Okay. So then we have access the recording on my YouTube channel. It says recording on YouTube, Adam Sapa. Just look up my name, Adam Sapa. The recording will be there after. Do we set every node to infinity and do the same thing? Yes. You set every node to infinity, has a weight of infinity, and you start there. Yes. So then we have next one was t to x. We already said that. T to y is 6 minus 4 is 2. So y has, sorry, t to y is what we're doing. Sorry. T to y is 6 plus 8. 6 plus 8 is 14, not better than 7. So we don't change it. T to z is 6 minus 4, which is 2. So the weight of z is 2, and we have a predecessor of t. Right? And then also I should fill in s has a distance of 0 and a predecessor of null. Right? Because there's no predecessor to s, it's the starting node, and has a distance of 0 because it's right there. And I'll spare you the time, but you just keep going through this over and over again until, so repeat until you go through entirely once without making any changes. Alternatively, I'm pretty sure, which is the exact same thing, you do it v minus 1 times. The number of vertices minus 1. Zs, you never change the source. You never change the source. But anyways, Zs would be, so Z would be 2. 2 plus 2, right? Zs, 2 plus 2 is 4. It's not better than 0. Right? Null. No, it means null. But there's not really enough room to write null. This. That's smaller. Can I make this smaller? There you go. There we go. Okay. What if Zs was -3? Then you would have a negative loop, right? You would have a negative loop there, and you would, yeah, what would you do in that case then if you had a negative loop? I know Bellman-Ford deals with negative loops, but how exactly? Let me see if I have an answer. Let me see. I don't know if I have an answer. Yeah, you would have a negative loop. I don't know. Does anybody have an answer for if there's a negative loop, what happens is the relaxed procedure should be false. After v minus 1, the relaxed procedure should be false. So you're saying that if you end up doing more than v minus 1, iterations, there's a negative loop and you should stop and there's something wrong. Okay, that makes sense. So repeat until you go through v minus 1 iterations. If you were to do another and an edge length continues to, sorry, a node weight continues to change, there is a negative loop inside the node and what? And stop? I don't know. Sorry, not inside the node, inside the graph. And just, I guess just don't do more than v minus 1 iterations. No. Just returns negative cycle true or something like that in pseudocode. Yeah, I remember that. The pseudocode just returns a Boolean that like negative cycle is true. Y is y minus x minus 3. Y is y to x to because an x would be 4. No, the graph is not done. You keep doing this. Let me tell you what the answer is after all this. Yeah, I'll answer that question in a second. Y to x is negative 3. Y to x is negative 3. Yeah. Oh, is y to x negative 3? Yeah, it is. It is negative 3. Yes. Sorry, I completely misunderstood your question. Yeah, but there you go. Y to x is negative 3. So, and stop to return true. I can't spell. True or negative cycle. Okay. This is not done. I'll tell you what the final answer is though. Let's just say you keep repeating. And you have, after all that, you will get, I don't know where I put it. You will get 0 to x, 2x 4 y 7 5. That's not 5, that's s. Negative 2. There you go. That's the final thing. Okay, guys, I'm sorry to say I have to get going. I teach like normal, not university. I teach like high school at 7:30, so I do have to get going, sadly, at 7:28. But thank you guys so much for joining. I really appreciate it. Good luck on the exam tomorrow. I'm sorry I couldn't get through all the content, not even close to all the content I wanted to get through. But thank you guys so much for joining. I really appreciate all the support here. I hope it was helpful. These notes, this recording will be posted immediately. And then I'll post it on my YouTube channel, which is here. I'll post the link to my YouTube channel here quickly. And then the notes will be in the description. And if I forget, then just please someone tell me. But the notes will be in the description. So here's the link. There's the link to my YouTube channel. The video will be posted there. Good luck, everybody. I hope everything goes well on the exam tomorrow. And if you have other exams, you probably do have other exams coming up. So good luck on those as well. Take care, everybody. Have a good night. Be here for 10 more seconds until I stop recording.